There we go. Okay. Back here for a new day. We have quiz 4 on Wednesday, and then we have our next exam, our first exam, on the following Monday. So it'll cover chapters 1 through 4. I'm hoping to get all the way through 3 and part of the way through 4 today. And then we should be able to finish up 4 and then have a little bit of time for review. If not, I will post review over chapters 1 through 4 on the YouTube channel. Yes.
Are you going to have a review with what's going on with the homework? I feel like you said something.
One is already up there. Chapter 1 is already up there, and chapter 2 should be up there tomorrow.
On your YouTube channel?
Yes.
Okay.
Yeah, it's under it's the one that is associated with its class. You hit the full videos on the Canvas page, and that should take you straight there.
Okay.
Might have a separate, and I don't want to do a separate. Well, I could do a separate playlist for homework. That would might be easier to find. So, okay, can somebody just try the chat online, please, so that I can see what people are there? Got like 22 people at home. That's not bad. Okay. So what I'm going to do is I'm going to go ahead and, oh, thank you. I'm going to share my screen so that everybody can see the slides. Minimize that and move this over slightly. Okay, so where we were last time, we were talking about Bronsted-Lowry acids and bases, and we're talking about how to tell which way the reaction is going to go. And what we did was we figured out what the acid was on the reaction side of the equation, and then we figured out what the conjugate acid was on the product side of the reaction. And all we had to do was to compare those two acid strengths, and you were always going to go to the weaker acid. Higher number, weaker acid. So that's how we got there. But now I wanted to shift gears here and talk to you about how the different things that, I'm going to move this out of the way, the different things that change whether something is acidic or not, okay? So there's a total of 4 things we're going to talk about. The first one is the element itself. And so the reason we're going to talk about the element itself is because it has something to do with size and electronegativity. So we're going to talk about that first. The second thing we're going to talk about is hybridization. So in hybridization, the hybridization on carbon will change the acidity of the hydrogen attached to those carbons. So we're going to see that in our trend table. The other thing we're going to look at is resonance. The more resonance structures you can draw for moving that a negative charge on the conjugate base around, the more stable it's going to be, because you can spread that charge out over more atoms. And resonance. And then the last thing is what we call inductive effects. Inductive effects. So element really has one of the highest contributing factors, followed by hybridization, resonance, and inductive, kind of in that order. So the first thing we want to look at here is, what do I mean by element? Okay. So if we look at our elements on the periodic table here, we told you that to increase the electronegativity, you go over and up, making fluorine the most electronegative atom, okay? So when we're thinking about acidity, we need to do 2 approaches. Number 1, we want to go across a row, we can compare all of those. Or we can go down a column and we can compare those. So let me do the first one first, which is along a row. So if we look at the row 2 here, we have carbon, nitrogen, oxygen, fluorine. Which is most electronegative? Fluorine. Okay, so the first trend is it goes with electronegativity as you go down a row. So if we look at carbon here, it has a pKa of 48 if it's carbon hydrogen bond. Nitrogen has a pKa of 38, and then water has a pKa of right around 16. And fluorine, as HF, has a pKa of 3.2. So we see that the acid strength is increasing as the electrophilicity increases, the electronegativity increases. Okay, now, and they're all about the same size atoms. So this trend works really well, increasing in this direction here. Okay, now let's go down a row. And if we go down this row, we have fluorine, chlorine, bromine, and iodine. Notice the trend is backwards. The fluorine is the most electronegative, but it goes in the other direction. So what's happening there? Why is it going in the other direction? And it has everything to do with the size of that atom and how long that bond is between the hydrogen and the halogen, okay? So if we look at down a row, down a column, we see size as the dominant factor, okay? And so we can compare everything in a row and say, oh, look, this is 3.2, that's barely even acidic. It's not even a strong acid. But then it goes to 7, 9, and then iodine being the most acidic at -10, okay? And that has everything to do with the size of it, not the electronegativity. We can see that same trend if we're going down this row with oxygen. Oxygen, sulfur, selenium, right? They're in the same place. They have about the same electronegativity, but their size is increasing. As you add an electron shell, the size gets bigger and bigger. And so we see the same trend. We see 15 drops down to 7, and then the selenium acid would be almost 4. So we're seeing that the acidity is increasing with increasing size. So the longer that bond is between the hydrogen and whatever you have, the more likely it is to give it away, i.e. the more acidic it is, okay? And if we look, we don't, and so if you're gonna do just electronegativity, go across a row, go across. If you're looking at size, you're gonna go down a column with increasing acidity. All right, questions on that? Okay, so now that we have the elements, yes?
If you're looking at electronegativity like vertically, would like chlorine be more electronegative?
Fluorine is more electronegative than chlorine.
Yes.
And so the trend is backwards, right? So in the columns, what we do is when you're going down, size is the dominant factor.
Okay, so
Because it's one down, it's a much bigger atom. And then one more down, it's a much bigger atom. So if you are comparing negativities, if they're the same, is one bigger than the other? Is one on another row down? That will tell you which one's going to be more acidic. No, electronegativity goes to fluorine. Fluorine is the highest in electronegativity. And so if we just went along this row number 2, then yes, it follows the trend. Carbon, nitrogen, oxygen, fluorine. But we can only compare the same stuff within that row because they're all about the same size. If we're dropping from one row to the next, now it's not electronegativity, it's size. Size dominates as you get bigger. And size is, the bigger it is, the more acidic it is. Okay? So those are the 2 trends we have here. And so it's important. It's similar to electronegativity, but different. So make sure you compare those 2. And so because we compare both of those 2 as number 1, let's move on to hybridization. And I told you that when we looked at the chart of things to know, which will include sp3 hybridized carbons, sp2 hybridized carbons, and sp hybridized carbons, we'll see there's a change in the electronegativity and the acidity. So if we go to sp3, and then we look at sp2 and sp, those are the 3 hybridizations we have on carbon, right? And in the case of the sp3, we have one s orbital, and it's the small round one, right? And the small round one is closest to the nucleus. And so it's going to hold things better with that s orbital. Okay, in the sp3, we have one s orbital spread out over 4 equal orbitals. So it's 25% s. 25% s. Okay, so if that's true, Then what about sp2? What about sp2? We have one s orbital spread out over 3 orbitals. So that makes it 33% s. Percent s. And in the sp, we only have 2 orbitals, one s, one p. And so that's 50% s character. Okay, so how does that go along with our pKa's? Well, it turns out that your 25% s character has the pKa 50 to 60. So that's a really weak acid or strong acid.
That's a very pKa.
Yeah, with that pKa. Very, very super, super weak. Okay, so it wants to hold on to that hydrogen really, really strong. Okay, let's look at this right here, the 33%. So when we change that hybridization, we change the shape. And it turns out the pKa of this is 44. So is that more acidic or less acidic than the previous one? It's more acidic. It has more S character. It's more acidic. Okay, let's go to our last one. It's 50% S. pKa is 25. Much more acidic. Okay, so that hybridization changes the acidity on carbon hydrogen-based acids. Okay, and so we'll see this trend again in another table we have. So if we actually jump back to this table right here, when we looked at the strong acids right here and then the carboxylic acids here, but then we had the alkenes, and the alkane. So this is the sp, this is the sp2, and this is the sp3. You see that trend. So hybridization controls acidity on carbon-based acids. Okay, yes.
Why is that? Is it because it holds electrons? Like why?
The electrons that get left behind are held tighter to the nucleus. Remember, when we transfer a proton, the electrons stay behind, right? So the electrons stay behind. And so if you can better stabilize those electrons that stay behind, it's more acidic.
Okay.
Does that make sense?
Yeah.
Okay. And we're gonna see that demonstration again when we talk about conjugation. So that's hybridization. And let's talk resonance, not conjugation, resonance. In the case of resonance, the more delocalized your anion is, your 2 electrons that stayed behind, the more acidic it is. Let's see about that. All right, so I'm going to let me just draw ethanol here. OH, and it has 2 lone pairs right here. And let me draw those electrons there. So if this hydrogen leaves, it acts as an acid. If the hydrogen leaves and goes away, these electrons are going to kick in here. And so we're going to have oxygen with a total of 6 electrons around it and a negative charge, right? So that's why ethanol is acidic. Okay. So, but let's look at acetic acid instead. Right here. In acetic acid, if we were to do that same thing where we're going to pull this hydrogen off, right here, we're going to generate the first resonance structure right here, but then there's another resonance structure where we can have that negative charge on the oxygen up here. So we'll have these electrons kick in, these electrons kick out, then these electrons kick in, then these electrons kick out. We go back and forth. So it's spread that negative charge out over a wider number of atoms, okay? So this is only on the oxygen by itself. This is on 2 different oxygens. This pKa is 17. This pKa is about 5. Okay, so that's the big difference there. The resonance is telling us that we can be much more acidic because it'll stabilize that negative charge. Just like in hybridization, we're stabilizing that negative charge with those held in tight orbitals, that s orbital. Okay. Questions on resonance. Okay, so the last thing is a little harder to describe. It's called the inductive effect. And in the case of the atom, that's the hydrogen bound directly to that atom, like HCl, right? And its sizes. And then in the hybridization, again, it's the hydrogen bound directly to the carbon that's hybridized. In the inductive effect, we're not talking about the atoms directly bonded to where the hydrogen's being removed. We're talking about 1, 2, 3, or even 4 bonds away. So it has to influence by pulling electron density through bonds. And that's the inductive effect, is it's pulling electron density through bonds. It's not directly attached. So what does that have to do? Well, if that's true, we have bonds, right? Our carbon bonds with anything electronegative is going to give us a polar bond, right? The more electronegative atom is going to pull those electrons there. So every polar bond is going to have this little tug on it, right? So if we to our acetic acid here and added I think I want to add bromine, but I'm not sure. Yeah, we're going to put a hydrogen here first. When we look at our acetic acid by itself, this has a pKa of about 4.7. Okay, with this carbon hydrogen and this carbon bond here. Okay, so is that carbon bond polar? Not really. Is that carbon hydrogen bond polar? Not really. So there's no plus or minus effect on it. But if we were to take that and add an electronegative element to it, like bromine, so now we have polar bond going in this direction, and inductively, it's generating a slightly more polar bond between the carbons because it's pulled some of that electron density away from one of the carbons. And therefore that carbon's slightly electronegative, more electronegative than it was, and pulls away. So now that we're doing this two things, our pKa drops to 2.8. 6. Okay, just that one polar group. And then if we keep increasing the electronegativity, I'm going to jump over here to fluorine. This is going to be 2.66, the pKa. Okay, so the inductive effect is it drawing electron density through bonds to a more electronegative atom. Does that make sense? Now that you have these electronegative atoms pulling electron density away from the negative charge that's going to be formed, it's more stable. Therefore, it's more acidic. Okay. But how close do you have to be? Well, you have to be pretty close, actually, because let's just have, again, let's draw this over here. I'm going to change this up, and we're going to draw a slightly larger carboxylic acid. This still has a pK around 5. It's just like acetic acid, just has a longer chain. And if I was to put that bromine right here, we would see the pKa of that would be about 2.9. So if the bromine was here, it'd be about 2.9. Okay, so what's going to happen if I move it over one carbon atom? Let me now move the bromine way over here. So instead of drawing electron density through this bond and this bond, it has to draw electron density through this bond, and this bond. So what's going to happen to pKa? The acidity is going to increase, or the pKa? Okay, so the pKa is going to go up because it's less acidic. It's being less stabilized by having those electrons pulled through the 2 bonds. It has to pull them through 3 bonds. So when our bromine moves to here, our pKa goes to 4.1. And if we move it over one more, it goes up again to 4.6. And if we move it over one more, it's going to go back to just like it wasn't there at all. So proximity is important here. You have to be, the closer you are, the more it's going to affect the acidity of your product. Okay, so we have 4 things we have to know about. And they are first, the element itself. Is it electronegative and how big it is? Those are the two most important things, okay? The second thing is inductive effects. Inductive effects are things not directly influencing that, but pull through bonds. The third thing is resonance effects. The more resonance structures you can draw, the better. The more acidic it will be. And then the last thing is hybridization. And this is most important for you to remember those in the hydrocarbon series. Alkanes are sp3 hybridized. Alkenes are sp2 hybridized. Alkynes are sp hybridized. And it gets more and more acidic as you go to that higher and higher S character. All right, questions? Okay, so that gives us up to our more common ones. The ones we've known love, you know, HCl, HBr, those are really ones we're familiar with, right? But there are some organic ones that we need to become familiar with. So all of the carboxylic acids in general, so you can have any R group here and an OH, those tend to be the most acidic of our organic compounds. Okay. But if we change the structure a little bit and do a derivative of sulfuric acid, we can actually get a very strong acid out of this right here. So this right here, is that CH2 on the drawn model? Yes. So this has a pKa of around 5. This has a pKa of -10. Ooh, why would it be so different? Why would it be so different? Oh, -7, sorry. Well, we have three things going for it. Number one, it's a bigger atom. Number two, you can draw resonance structures across all three of those oxygens. You can also draw resonance structures in this benzene ring. So you have the big atom working for you, you have resonance structures working for you, you have a lot of places to move those electrons. So it's going to be much more acidic. And so that's one of our strongest organic acids we're going to do. And it's called Paratoluene sulfonic acid. So this has this toluene, sulfonic acid, and it's usually labeled as TSOH, big T, little s, OH. And the reason I say that is we use it as a catalyst, an acid catalyst. So you're going to see that TSOH, so make sure you make a note of it, please. Okay, so now that we have, those are more common organic acids, let's talk about a few organic bases. I said before that if we had an alcohol and we pulled a proton off it, it would be a conjugate base because we've removed a thing. So if we did water, we would have OH, hydroxide. And you would have to counterbalance that with some kind of counterbalancing ion. And if water has a pK around 15. Well, alcohol also has a pK of just above 15, 16. So we can probably remove that one and turn that into a base too, right? So if we had just ethanol and we removed one of those hydrogens off here and we put sodium here, that would also create a base. Are these strong bases or weak bases? Well, what were they acid-wise? They were very weak acids, right? And very weak acids become very strong bases. So we're starting to use really strong bases to come in and remove protons for us. And we can even go a little bit higher than that. And this is a very common one we're going to use a lot too. And this is T-butoxide. So it's tertiary butyl. And we've taken the one proton off the alcohol. And so a lot of the times it's, again, counterion potassium here. T-butoxide. So T-bu-O-. That's a cursive T, by the way. So this is a very good base because it's a very poor acid before we remove the proton, and that makes it a very good base otherwise. All right, questions on that? So those are all oxygen-based bases we're going to use in organic chemistry. We can also use sodium-based ones. And the first one, sorry, not sodium, nitrogen, I want to do is this one right here. This negative charge on nitrogen here is a really strong base, okay? When we look back at our pKa's on the ammonia here, we'll see that ammonia has a pK of 38. Yes.
Can you use something else?
Uh-oh. Thank you. All right. Don't verify anything online. Okay. So, let's see. All right. So, we have our nitrogen can also be a strong one. And we're going to use another one, not this semester, but next semester, where we actually take diisopropyl amine, put an anion here, and we usually have a lithium as the counterion. We call that lithium diisopropyl amine. And it is a really strong base. The nitrogen being more nucleophilic than carbon, it's going to be more acidic than carbon, making it more basic. And so it is going to be a nice base. And then the last base I want to talk about on this slide is that one. What in the heck's that? Okay, we have a hydrogen, but it has a negative charge. Okay, so imagine, if you will, hydrogen. It has one electron shell. It can put 2 electrons in there. When it's being transferred around as a proton, it doesn't take any of those electrons with it. It always uses the Lewis base's electrons. Okay, so that's no electrons, so it has a positive charge. If it's neutral, it has 1 electron, 1 proton, and it's neutral. But it has a place for 2 electrons in its outer shell. So if you put an electron in that outer shell, fill that outer shell, it's going to have a negative charge. But again, it's going to be a very strong base, and we call that hydride. And it's usually with a sodium or a potassium hydride. Okay, so that being said, where are, I have a picture here. There we go. Aha. That being said, that lets us see where our, okay, not that one. No. All right. 2 p.m. There we go. Okay, so that lets us see where we have these strong, strong bases. Okay, so if they were weak acids and we take a proton off them, they become strong bases. And so we have oxygen-based systems, sodium-based systems, and hydrogen-based systems. All right, so, but what about, HCl and HBr, right? Those are strong acids. Well, what happens is that if they were strong acids, that makes the fluoride, chloride, bromine, and iodine ions weak bases. They were such strong acids, they don't want the proton anymore. They are weak bases. So really, most of the time we can't, these are going to be just removed by a stronger base. We'll not see them any at all. Okay, so what that means is that, if after you've reacted something on your system and you put out a halogen as a leading group or on the side, it's not going to go backwards because it's not strong enough. It's too weak a base. Okay. Now, one of the most basic of all of these is a negative charge on carbon. Negative charge on carbon. Think about it. The pK of the sp3 hybridized carbon is 60, 55, and 60. So it's the least acidic thing we have, making it the most basic of our anions. And it can be sp, sp3, or sp2 as the anions here. So these anions are our strongest bases. Okay. We can also use neutral nitrogens. Why can we use a neutral nitrogen? We've used nitrogens with anions before, but what about something that's like let's say we just have 3 R groups on here. Why is this a base? Oh, let me draw the lone pair here. Ooh, wait, hold it. Don't all Lewis bases have lone pairs or negative charges? That means that this is a base. and it is basic, and it's going to be slightly more basic than things like water. It's going to be more likely to pull off protons and do that. So when we think about this, we want to see that the pKa of, let's see, can we do a pKa of this? No, because it's a base. If we protonate it, it becomes a conjugate acid, right? Well, the pKa of the conjugate acid is 10. So if we reacted this with water, H2O, on this side of the reaction, the water is the acidic one because it has the pKa of 15. On the other side of the reaction, now that we have the nitrogen carrying this hydrogen, R, the pKa of this conjugate acid is 10. So which way is the reaction going to go? We always go to the weaker acid. So it's going to go back toward water and the amine. But if we were to do something with HCl, the pKa would now be -7. And the pKa of the conjugate acid is 10. So which way is it going to go? It's going to go to the weaker acid. So it's going to go to the protonated nitrogen. All right, questions on that? So think about that lone pair as the one that's going to reach out and grab that hydrogen. And now that it's an acid, you can compare the pKa's of the conjugate acid and the acid to know which way the reaction went. All right. So in the case of pKa's and such and non-aqueous solutions, we're always going to use that trick of looking at what the two acids are and see which direction the system's going to go in. So for example, if we did one of our acidic hydrogen carbons, triple bond, and then a hydrogen here, and then we reacted with something, and let's do sodium amide, which is that one of those strong bases we talked about. That's a 2, that's a negative charge. If we reacted with this, this is our base and this is our acid. So our pKa of this is, pKa is 25. It's one of the ones you're going to memorize, by the way. And if we go to this side, now we have carbon, 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 triple bond plus an anion, plus this newly protonated nitrogen species. The pKa of this is 38. Okay. So which way is the reaction going to go? We have this pK is 25, pK is 38, which is the weaker one. The 38. So that means the reaction is going to go in this direction, giving us our anion on carbon. Can we do that same thing with hydroxide? I don't know. Let's see. H, and we do hydroxide right here. So the conjugate acid of hydroxide would be water. So H2O, which has a pKa of 15. And this still has a pKa of 25. So is hydroxide going to deprotonate that carbon? No, because this is the stronger acid. So this reaction doesn't go. In fact, anytime you have a carbon anion, you have to make sure you don't have any alcohols or water in there because it'll react with that first. So that's a very important thing you'll see is a lot of them will do two-step reactions and the second one will be water. But that's just because we want to get rid of those anions. Okay, so that means we have to be very careful about what solvent we use these in, right? We can't just use water and alcohols. We have to go for hydrocarbons or things that don't have as acidic hydrogens. So we have to be, oh, yeah. All right, so I think I wanted to go back and look at this one thing, and then I should, okay, not that one, this one. Okay, so these are the pKa's you need to know. Okay, I put a thing on Canvas saying pKa's you need to know. These are the ones you need to know. The first and foremost is carboxylic acids. They're all around 5 unless you have inductive effects, and then they get more acidic. The next one is phenol. So I'll draw phenol for you. It's basically an alcohol on a benzene ring. Why is phenol more acidic than ethanol? They're both oxygens. The oxygens are both carrying the negative charge. The benzene ring, right? We can draw a resonance structure where the negative charge can move around that benzene ring. So resonance is giving us more acidity in that. So resonance gave it more acidity in the carboxylic acid, but it also does it in the phenol. Now, once we get to the alcohols and water, that negative charge stays on the OH, stays on the oxygen. So it's less acidic. And that gives us our next set. Alcohols and water are right at the 15 mark. So we move from 5, 10 to 15. And the most acidic hybridized, SP, is 25, SP2, 45, SP3, 50 to 60. Okay. This table is on Canvas, so this is what you need to remember. Okay, before I go any further, I want to go ahead and take roll. And then do your seat number and all that stuff. All right, done, and then go back to here. All right. So now that we have this kind of thing where those carbon anions are really, really strong bases, we can actually probe like the mechanisms of some of these reactions by taking that advantage of this strong anion. We know that that strong anion is going to react with water because of the acidity of water. So if it just reacts with water, we're going to put a hydrogen back where that negative charge was. Okay. But what if we wanted to probe it for by NMR or some other technique where we could look at a different isotope? Turns out that if instead of using just regular water, you use water with one extra neutron, or you use hydrogen with one neutron in it, it's called deuterium. It's heavier. We can see that by instrumentation. And if deuterium, D2O right here, reacts with this anion, it's going to show us where that anion was. We're going to see that deuterium exactly where that anion was. And so in this case here, we can probe saying, oh, was the anion, wow, it just does not want me to write a D here. We know exactly where that negative charge was because that negative charge is exactly where that isotope goes. And there's even one more heavier one called tritium. It actually has 2 neutrons in it and it's radioactive. But if we have our anion here, we can do that same labeling. And so we can use this to our advantage, that fact that it does suck up anything with acidic protons to probe the mechanism of our system. All right, questions on that? Okay, so I set up now, we have acid base, right? And the reactions go because they want to go to the weaker acid or the weaker base, right? That's how we're doing it. So let's talk a little bit about the difference between thermodynamics and kinetics. In the case of thermodynamics, that describes the energy of the products versus the reactants. If the products have less energy, the reaction is thermodynamically favored because you want to go from high energy, high acidity to low energy, low acidity. So you're doing the same kind of thing. Now, in contrast, you can have a reaction where it goes very quickly and makes a high energy material. Okay, that's kinetics. Kinetics is the speed of the reaction. Okay, just because a reaction goes doesn't mean it's thermodynamic or kinetic. You have to look at the 2 components. Compare the products and the reactants energy-wise, and then see how fast the reaction went. Okay. So we have to think about how this plays into our equilibrium, our acid-base equilibrium and reaction equilibrium, is that the equilibrium must favor the products. Okay, the lower energy material, the lower acidity thing, okay, must favor the products. That means we're thermodynamically going less in energy. You're going to that process. Now, the rate of the reaction for an acid-base reaction is almost instantaneous. It's very fast. Does that mean it's going to overshoot and make the less thermodynamically favored product? Probably not. But when we talk about the kinetics of the reaction, we have acid-base reactions we're going to be doing later that are slower. They just have to be fast enough to be useful. They don't have to be instantaneous. You can have a reaction last over a month. I mean, I'm sorry, over a day or 2 days. You don't want a reaction that takes a month to get the products. So that's kinetics. That's the kinetics aspect of it. Okay, so that being said, how do we get to this thermodynamic equation? Well, we start thinking about it as the equilibrium, right? We did those KAs, and that was kind of an equilibrium problem where we looked at the concentration of the proton in its acid form and its conjugate acid form, right? So what we're going to do here is we're going to use that same concept, but instead of having acids and base transfer, we're just going to have compound A react with compound B to go to, well, maybe it'll go back this way, we don't know yet, compound C and compound D. Okay, so in theory, to get compound A and B to go to compound C and D, there has to be some energy, some difference in energy, preferably such that these are more stable. Well, that turns out we had to measure this. And so if we have our equilibrium is just like it was before, our products over our reactants. Okay, products over reactants. Why? Well, you're hoping it to go to product, right? And so your equilibrium constant, if it's going to product, is going to be more positive. It's going to be higher. So we're going to have product over reactants. So basically, that's the concentration of C times the concentration of D over the concentration of A over the concentration of B. So that should look very similar to that pKa one we did, right? So what we want to do now, the fact that the products are on top, we want the products to go, we want it to go to products. We want to think about, well, what can we do if the reaction goes to its equilibrium and it stops? Well, it turns out Le Chatelier says that you can disrupt the equilibrium. How can we disrupt the equilibrium? Well, if we have concentration of products and concentration of reactants, and it goes to maybe, let's say you get 100 of these and 100 of these, and you still have 50 of these and 50 of these. That's where that's where it stops, right? You can add more of something and get more of the products. You're disrupting the system. So your equilibrium constant is actually based on where it would stop naturally, but you can perturb the system to get it to drive it to products. And one of the best ways to do this is, let's say one of your products here, let's say D is instead of a compound, well, let's just say it's water. Okay, and so by equilibrium, it'll go so there's so much water in that solution and it won't go any further. Well, water boils at 100 degrees. We could boil it out of the reaction mixture. That perturbs the system. We're going to get more product C, because we've taken away one of the elements that was controlling the equilibrium, and therefore we can force it further and further to products. This happens a lot in reactions where you'll see people boiling water out of reactions, and you'll get from like 50% yield if it was at equilibrium to like 100% yield because you drove the water off. That's what's perturbing the system when you talk about these equilibrium. Does that make sense? Okay. All right. All right. So that being said, that means an equilibrium constant over 1 favors products, because the more amounts of the products are on top, right? So that's the bigger number. So it'll favor products. And so if we favor the products here, it means the equilibrium will lie to typically the right side of the reaction, toward the product side. And this reaction could be useful. Again, there's a kinetic element. If it's too slow, it might not be useful. Right here. Now, if the equilibrium constant is less than 1, that means it prefers the starting materials to the two products you're forming, okay? That means that it just wants to stay as starting materials. And we draw the arrow going the other direction, to the starting material side of the reaction. And these reactions tend to not be as useful. The only time you can make a reaction like this useful is by perturbing the system, taking away one of the things you're forming to make it go closer to products. All right, questions on that? So when you think about it, you know, products are on top. The bigger that number, the more likely it is to have making products. Okay, so let's look at that from an energy perspective. I want to talk about the Gibbs free energy of the system. Okay, and so basically the Gibbs free energy is telling you the difference in energy from starting materials to products. So delta here means difference. Okay, and it's going to be equal to the Gibbs free energy of the products minus the Gibbs energy of the reactants. Okay. So what does that mean? If we have more reactants than products, if we have more energy in the reactants than the products, we're going to get a negative number. If we have more energy in the products than the reactants, we're going to get a positive number. Okay, so what does that look like? Well, okay, let's look at the energy of the products. And it's higher than the energy of the starting materials. So this difference in energy right here, going from starting materials, SM starting materials, to products, is a positive number. So that means, sorry, that's not right. Yeah, it's a positive number, meaning that it took energy to do. So the products have higher energy. Okay, is that a favorable way to do your reaction? To have it be higher in energy? Probably not. But if we had it where our Gibbs free energy of our reactants was higher than the Gibbs free energy of our products, it's going to give off heat. Our Gibbs free energy is going to be, let's see, this is greater than this, so it's going to be positive. No. Oh. Okay. Products minus 3. Yeah, there we go. So what we're going to see here is that if the energy of your starting materials is higher than the energy of your products, it's a favorable reaction. It's going to want to lose that energy and go to the more stable form. Okay. So in this case here, the equilibrium will favor the starting materials. It just doesn't want to go. In this one here, it'll favor the products. Okay, so Gibbs free energy, that's kind of a weird little thing. You know, it's kind of conceptually difficult. Well, let's make it a little easier and kind of compare it to our equilibrium constant. We did that with our acids, right? We got our acidity constants and turned them into something easier to play with. And if we go with the changing this up a little bit, we can actually relate our Gibbs free energy. The change in Gibbs free energy is equal to a constant minus 2.303 RT log equilibrium constant. Remember when we had the pKa's, we did the log because they were such big numbers? We're going to do that same thing here. But the important thing here is that this number is a constant. This is our gas law constant. This is our temperature in Kelvin. Okay. So a delta G in here, if your equilibrium constant is negative, then your log there is going to give you a positive number. If your log pKa is negative, it's going to give you a positive G, because this negative sign multiplied by this negative sign equals a positive sign. But if your delta G, if this equilibrium constant is positive, you're going to have a negative number, and so you'll have a negative delta G. Okay, so what does that mean? That means that if your Ka, I'm sorry, your Keq is going to give you a negative log, it wants to go to products because energy is released. And if your negative, so the positive change, we have a positive change in energy. Okay. And we'll make our, no, I'm sorry, makes Gibbs free energy negative, meaning energy was released. If our Keq is, if our log Keq is negative, that's going to make our Gibbs free energy positive, meaning energy was absorbed. We've added energy to the system. We haven't given away energy to the system, and therefore it is going to favor the reactants. Okay, questions on that? Okay, and I'm still talking about this elusive Gibbs free energy, and what does it mean? Well, we're comparing the energy from the beginning to the end. Can we relate that to something a little more substantial? And yes, we can. And what we're going to do is we're going to add a couple more elements and see if we can't relate that to bond energies, okay? So the first element I want to do is I want to talk about entropy. Okay, Gibbs free energy is the difference in energy between products and reactants, right? Entropy is the difference going from something that's more ordered to less ordered. So if you have positive entropy change, you're going from one thing to two things, because two things is inherently more disordered than one thing. So we want to look at that is that when we have one thing and we break into the two things, we have increased entropy in the system, okay? This becomes very, very apparent when you have high temperature reactions where you're actually blowing apart, like taking one molecule and turning it into 50. This is really a lot more entropy, and so it's really important to take that into account. The other way to go, though, is if you had two molecules and you put them together, your entropy actually went down. You went from two things to one thing. That's more ordered. There's less disorder. So that means that we can really have a nice positive effect or negative effect on the entropy just using that two concepts. Now, there's also a big effect at higher temperatures of entropy, because the hotter you are, the more disordered you are. Think about liquids versus gases. Gases are more disordered. So the higher in temperature you go, the more entropy plays a role. Okay, so we have entropy now. We have Gibbs free energy, but we still haven't related it to bond energy. Why are those products more stable than the reactants? So let's give you one more equation right here. And what we're going to do is we're going to give the equation that relates all that together. Okay, so the change in Gibbs free energy is equal to delta H minus T, which is temperature in Kelvin, delta S. Okay, so this is a nice little thermodynamic thing, but what's H? H is enthalpy, okay? And when we talk about enthalpy, we think about the energy in the bonds, okay? Every bond you make has energy in it. And the stronger the bond, the more energy it has in it. So if you started with a bond of A and B over here, and you change it to a bond of B and C, they're going to have different energies. And so that difference in energy is our enthalpy. That's our H. So now we can take our Gibbs free energy and compare it directly to more stable bonds. If Gibbs free energy is positive, you have more stable bonds. And so that means that we can compare them directly. So let's look at this term then. So if we have T here as temperature in Kelvin. Oh, go ahead.
So if you go from SP3 to SP, does that mean that the entropy is higher? The bond is higher?
Well, just hybridization doesn't, you have to make and or break a bond. So what bond are you making and what bond are you breaking? So for example, in our elimination reaction, we broke 2 sigma bonds and turned it into 1 pi bond, right? So we have to take away those 2 sigma bonds. Those were some certain energy. The pi bond has a different energy. So now the difference between those 2 things, then we would add all the bond energies together and see which one is higher or lower. So,
it's positive and it's-
so if, and actually I'll tell you that the alkene, the double bond, is higher in energy than the alkane. So that means we had to put energy into the system, it absorbed energy. Okay? Spoiler, but okay, there we go. So what we have here is that we have this T thing. And so in most cases, you know, T is around 100 degrees and entropy typically doesn't change too much. It either goes from 2 things to 2 things or 1 thing to 1 thing. So this term right here really doesn't change very much. So that means we can actually say that delta G, which is not really, which is what we can measure, is approximately equivalent to delta H, the summing of all the energies and all the bonds. Okay. So obviously we aren't going to do any calculations on this, but when we will do bond dissociation energies, and I'll show you how that kind of plays a role. Okay, so what this means is with this simplified setup, we have that if entropy is positive, then products are more disordered than the reactants. Entropy's gone up, we have more disorder. If the entropy is negative, we have less disorder. Now, what do we mean by less disorder? Well, we can start with something that is straight and break it apart into 2 things. That's more disorder, right? We can take something that is a straight and turn it into a ring. It has more order now because it has fewer modes of freedom to rotate around. We've taken away one of its modes of freedom. So it is more ordered. So we'll see that in our other entropy term. Okay, so thermodynamics is all about total bond energies. Kinetics is how fast the reaction goes. We would like to have reactions that give off Gibbs free energy so that the products are in lower energy than the reactants. That way we'll have a nice favorable reaction. Does that mean all reactions are that way? No, but there has to be something to get us to go up that hill. We need to have a higher energy starting material, or we had to add energy to the system some other way. And so we'll see that when we start doing our reaction diagrams of how the energy changes as the reaction progresses. Okay, so that being said, I want to stop this here and start on chapter 4. Okay. So in chapter 4, we're going to learn about nomenclature of organic compounds. Okay, nomenclature is just a systematic method of naming things correctly. And what we're going to find is we're going to start with about 5 basic rules, and we'll be able to name everything this semester and next semester just by adding additional rules. We're never going to change the rules, but we'll add rules to get to different things. And so when we do this, we use what we call the Iupac method, which is the International Union of Pure and Applied Chemistry. If I say not fast. And so we want to use this method. We want to use the step-by-step down. So you don't want to, memorize anything. Memorizing a name is not going to help, because if you don't know how it's put together, it's going to be really hard. And so the first thing we want to look at is that we have what we call our main thing, or our parent chain. And then anything that's not our parent chain is a substituent, something that's added to it. Okay, And so what we're going to do is we're going to come up with some really cool ways of finding our main chain and adding our substituents to it in a very precise, structured way. Now, in addition to that, besides the Iupac, I will be giving you some common names because they really, really are common, and that you need to have those common names memorized, like acetone. It's really 2-propanone. So we'll be able to give you names like that. Okay, so the first part of the system is actually naming the longest chain. And when you name the longest chain, you use the meth, eth, bute, prop for the first four. And then of course it's much more even with the penta, hexa, hepta, etc. So that number that's in there is the number of carbons in the main chain of what we're going to do. Okay, we're going to call that the prefix. Okay, now the suffix or the end of the word is going to tell us something about the functional group. In this case here, we only have hydrocarbons. We only have carbon-hydrogen bonds. We only have sp3 hybridized carbons, and therefore its suffix is ane. ane. So we can take a carbon chain of any length, let's take 12, and go dodeca, and then add the word ane to it. And now we know exactly that we have 12 carbons in our main chain, and there are no double or triple bonds. Does that make sense? That's a cool system, because now you know how many carbons you have, and now you know that you don't have any other functional groups. And if you had other functional groups, there'll be new words in there somewhere. So we can pay attention to everything that we have. But what if it's attached to the main chain? Well, we have a different nomenclature for that. And the reason we change it to recognize immediately that it's a substituent. You'll know that if it doesn't have the ane or ene or yne, if it has a yl, then it's a substituent to the main chain. So you take the number of carbons in that substituent, meth, eth, bute, prop, and add yl to it, and now it's a substituent. You're going to put that in the beginning of the name. So that'll be in the beginning of the name. Okay. So a lot of the common ones are like meth. There's no H, it's meth. Meth is, they have common little abbreviations. Meth, eth, prop, and bute have these combinations. And we usually draw them as little stick figures here. Okay. But what's that squiggly little line? That squiggly little line tells you that that's the main chain. That's the big one. And your little one carbon in this case is attached to that main chain. 2 carbons, 3 carbons, 4 carbons. Okay. Does that make sense? So now you have little teeny substituents along your main chain. Okay, so I'm gonna add another rule. So we actually have isomers. Meth and eth don't have isomers. Those are the only two you have. But by the time you get to 3 carbons, you can attach that group, that substituent, either by the end carbon at the end or by the carbon in the middle. And so we have 2 different isomers for that. And so if it's attached by the one on the end, we have it like here. So you can think of it, this is like the first carbon in the chain of the substituent. And this would be the second carbon in the chain. Okay. So if it's bound to the first one, we just call that the propyl group. That's the normal propyl group. But if it's an isomer, iso. And so the bunny ears, like that I like to call them right here, is our isomer of the propyl. So it's our isopropyl. Okay. So that's the propyl only has 2 isomers. You can do it the 1 carbon, the 2 carbon, or if you ended up at the 3 carbon, that would then turn it back into the 1 carbon. So you only have the 2. But what if you have 4 carbons? 4 carbons gets a little more complicated. And when we do the 4 carbons, we want to do 2 things. One, it's going to look a little bit like what we saw before. So in 4 carbons, it can be straight. We call that N-butyl. Okay. If we have the little bunny ears structure here, and it's bound to another CH2 right here, then we have the isobutyl. So isopropyl had the bunny ears, isobutyl has the bunny ears, but 1 more CH2 group. Now, We go over here, this is the second carbon on that chain. We call that sec butyl. So now we have normal butyl, isobutyl, sec butyl. The last one, we have 3 carbons on this carbon here. That would make it a tertiary substitution, and that tertiary substitution makes it tert butyl, tertiary. So you can recognize the structures just by how many things you have hanging off there. So those are the most common ones for butyl. In fact, those are the only ones for butyl. And the last one I want to show you is, I know I have like 10 minutes, right? Okay. Is the neopentyl. Okay, so imagine you have the tetrabutyl right here, and then you just add another CH2. And that's the last one. It's called neopentyl because there's 5 carbons and it's new. Neo. Okay. All right, questions on substituents. Okay, so we have main chain we have to worry about, and then we have substituents we have to worry about. So let's worry about the main chain and how to find things. So the first thing we want to do is we want to find that main chain. Okay, so we're going to call that our parent chain. That's the longest number of carbons we can have continuous in our system. And then everything else is a prefix or a substituent or a suffix, which tells us functional group. So we're going to look for that first. And then, so we're going to name that longest chain with that longest carbon number. So if it's 12 carbons, it's dodecane. If it's 16 carbons, it's hexadecane. So that's where we're going to get those names. Then this is going to tell us about functional group. And right now we only have one functional group we're talking about, ANE, hydrocarbon sp3 hybridized. And then the prefix tells you the identity, location, and number of substituents. So all the stuff in the beginning tells you where all the little stuff is. Then the stuff at the end tells you what kind of hydrocarbon you have and how many carbons are in it. Okay, so let's apply that rule to our system. Okay, the first thing we want to do is anything that's a substituent has to have that YL and associate with the number of carbons it has. Any parent chain has to have at the end alkane for now. Okay. Okay, so we want to look for that in our system. So how do we find our longest chain? Well, let's look at this one right here. Okay, so if we did, let's see, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 carbons that I can get that way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 carbons that way. Let's number this way then. Let's see. 1, 2, 3, 4, 5, 6, 7 carbons that way. So it's definitely not that one. And let's see, one more color. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 11. So 12 is our longest number. So we've now identified our parent chain as dodecane. 2 plus 10 plus 8. So now, but what about this one? This one's actually easier to see because the 12 carbons are right in a row. It's easier to see where the different system is. So do we all get how to look for the parent chain? It's the longest continuous carbon chain. Okay. And if there are no double bonds or triple bonds, it's ANE. AIM. Okay, that's rule number 1. Rule number 2 is if you have a choice by where the longest chain is, you want to do the one with the highest number of substituents. Okay, highest number of substituents. And the reason we do that is it makes it easier to identify them by their location. So we're going to do the highest number of substituents. So in this case over here, where you could have the main chain go along this side here, we would end up with 1, 2, 3 substituents. Okay, and if we rearrange that structure, we'd have 1, 2, 3 substituents. So we're not going to have this as our main chain right here because we'd only have 1, 2 substituents. So we want to use the one that has 1, 2, 3 substituents. Okay, so longest chain, greatest number of substituents. That's really, really good rules. The next rule is numbering. We want to number and identify the location of each of those substituents. And we want to do it with the lowest numbering system possible. Okay, so in this case here, let's look at this one here. If we number from the top here, it goes 1, 2, 3, 4, 5, 6, 7, 8. And our first substituent is on the 4, then we have 1 on the 5 and 1 on the 7 carbons. If we number from that side. If we number from the other side, our first substituent's on a 2, a 4, and then a 5. Okay. So which way should we number it? The bottom row, because it gives us the smallest numbers for our substituents. Okay, so that means if we were going to locate these, let's see, we have a methyl group here, a methyl group here, and an isopropyl group here. So we'd say there's a methyl group on the 2 carbon. There's a methyl group on the 4 carbon, and there's an isopropyl group on the 5 carbon. So those will be in our prefix, our attachment, okay? So when we do that, we want to go that, let's do that 2-methyl. So the YL tells us we have a substituent, the 2 tells us which carbon it's on, and the little dash here tells us that that 2 is associated with that function, that substituent. Now we have 2 methyl groups here, so we're going to have to do a 5-methyl at some point in time. And we have the, I'm sorry, yeah, and then, no, that's a 4-methyl, and then we have a 5-isopropyl. So those are our 3 substituents, okay? Now, what we can have with this is we can eventually add multiple of the same kind of substituent together. But the important thing here is we're not going to have any spaces, commas, or hyphens between letters. So you want the things to run together into single words, okay? So you only have a number hyphen for the substituent, then you're gonna have a hyphen, number, hyphen, substituent, then parent chain, okay? So now let's talk about adding these together, okay? If you have more of one of the same thing, you can add di for 2, tri for 3, tetra for 4. So we have 1, 2, 3 methyl groups on this chain. Which way are we going to number it? Are we going to number it from this direction, or are we going to number it to the left or the right? Yeah, because this is going to give a 2 and a 3. Well, 1, 2, 3, and a 4, plus this one. So this is going to give us our 2 lowest numbers. So we're going to number from that side. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 2. No, we have 3, 4, 9 trimethyl. And that's not how to spell tri. I was trying to, but that's no, sorry. That's it. Trimethyl. Okay. Now, if you have more than one type of one, you need to alphabetize them. Okay, we need to put them in a specific order. And so ethyl would come before methyl. Okay, but even if you had 2 methyl groups on there, so it'd be ethyl and dimethyl, you don't count the di, tri, and tetra in alphabetization. You only count the substituent itself. Okay, so that means when we do this right here, the ethyl is going to come before this dimethyl. And then there, if the group has a weird little group here, we're going to ignore any of the prefixes on that substituent. We're going to just ignore that and only do it the main substituent. So this would be 1, 2, 3, 4, a butyl. It's a, well, 4 carbon chain plus a methyl. So it'll be a methyl butyl substituent. So we're naming it for this part, the whole part, not just that. The only prefixes we don't ignore are iso and cyclo. So isopropyl, and when we do cyclo compounds, those you don't ignore. Everything else is alphabetized by the substituent carbon number names. Okay. Okay, so I'm going to review what we've done so far, and then we're going to head out today, and we're going to come back on Wednesday. And then we're gonna have, so you find the longest chain, right? You number the longest chain such that your substituents in the lowest places possible. Then you can alphabetize them. And then you add your di-tri-tetra after they're alphabetized. And so when we get to the end here, we will, I'll show you some examples on Wednesday. We'll just do examples. All right. Thank you very much. Any questions? Okay, I'm gonna go ahead and stop sharing and stop recording.
Does it